Welcome back. All right, we're learning about climate models here, and we're learning about them as the technique that we're using here is we're picking apart an argument that says this shouldn't work. We shouldn't be able to make models of the climate that can tell us anything meaningful about the future climate. And we said that part of the story as to why that argument was wrong is that weather and climate are just very different types of questions. We learned so far that numerical weather prediction, the forecasting of weather using models, is an initial condition problem. Sometimes called an initial value problem. That is really tricky. We have to have really good observations in order to make appropriate initial conditions that are input to the model. But it turns out initial conditions are by no means the only type of input that goes into a model. Another perfectly valid and important part of a numerical model is a set of inputs called the boundary conditions. Boundary conditions are external processes that are driving the atmosphere. And they are, even though the name is a little bit similar, they are completely unrelated to the initial conditions. The initial conditions are things that you're going to be forecasting, like temperature and pressure and so on. You're just getting the current values of them. But then what you want to do is forecast into the future. What will the temperature be? How will the temperature change? What will the pressure be? How will the pressure change? You start with initial conditions of those variables. Boundary conditions are external to that. They are external processes that are driving, in this case, the atmosphere. Things like, for example, the output of the sun. How many watts per square meter of sunlight are reaching the surface of the Earth? Okay, that is not something we're forecasting. That's something we have to tell the model. We tell the model this is how much energy is coming from the sun. The chemical composition of the atmosphere, in particular, like how much greenhouse gases there are. What are the abundance of the different gases in the Earth's atmosphere? We aren't predicting. Our climate models and our numerical weather prediction models aren't predicting how much fossil fuels we're going to burn. No, we tell it. We tell the model as part of the input, we're going to have a carbon dioxide concentration of this many parts per million, or we're going to have a methane concentration of this many parts per million, or whatever other chemicals you care about in the Earth's atmosphere. This is a boundary condition, to use the right term. It's something external coming in through the boundaries from the equations themselves. None of the 7 primitive equations are about forecasting how much sunlight reaches the surface of the Earth. None of the 7 primitive equations are forecasting how much halocarbons get emitted into the atmosphere. We have to tell the model that. Another one, albedo of the surface of the Earth, how reflective of the surface of the Earth. We change the albedo of the Earth by doing things like cutting down forests and putting in fields, or tearing up prairie and putting in a parking lot, and so on. Okay, the model doesn't predict that. We tell the model that. We tell the model as input what is the albedo of the surface at each location here. These are boundary conditions. And both numerical weather prediction models and climate models have to include these factors. But boundary conditions actually don't have a huge effect on day-to-day weather. Okay, if I started with the weather right now, but somehow magically, I don't know, due to a big volcanic eruption or something, doubled the amount of carbon dioxide in the atmosphere, that wouldn't actually change the weather over the next few days. It would change the weather drastically over the next few decades, as the greenhouse effect from all this new carbon dioxide added up. But realistically, things like the effect of the amount of carbon dioxide in the Earth's atmosphere, that doesn't change whether it's going to rain tomorrow or not. If the sun suddenly was 2% warm, emitting 2% more radiation than it is right now, we would notice that right away. It wouldn't, suddenly tomorrow would be really hot. It would take a very long time for that amount of heat to actually make a noticeable change to the Earth's climate. It wouldn't happen immediately. Yeah, we include those factors in our numerical weather prediction models. We actually include things like measurements of how much radiation is coming from the sun, but from day-to-day weather, that has virtually nothing to do with it. On the other hand, these factors all have huge impacts over the course of years and decades. In a numerical model of climate, if we increased the amount of radiation from the sun by 2%, heck, we could probably get the oceans to boil. Okay, it would just take, over the course of 100 years of the oceans getting a little bit warmer all the time. Yeah, the oceans wouldn't be particularly all that much warmer 3 days in, but 100 years in, the oceans are boiling. The oceans boiling is something that sometimes happens when climate models go wrong, if the scientist setting it up makes a mistake. So here's the deal, though. These so-called boundary conditions, things like that are external to the 7 primitive equations, like the albedo of the surface of the Earth, or the amount of radiation from the sun, or the greenhouse gases in the Earth's atmosphere. These things are actually all things climate scientists really understand pretty well. They are things that we have really studied, and we understand that when you change these things in the model, they change the climates that the models simulate. If you run the model with current, telling it the current amount of carbon dioxide in the Earth's atmosphere, and then you run the model a second time where you tell it twice as much carbon dioxide, you get a warmer planet. If you change the albedo of the planet, you change the temperature of the planet in the climate models and so on. We know these things happen. We know how these things work in the model, but the effects are not like incredibly sensitive to these changes either. It isn't like if I simulate, okay, the current concentrations of carbon dioxide in the Earth's atmosphere are right around 400 parts per million. If I say, now run a simulation where it's 500 parts per million, and I see, oh, the planet's a little bit warmer, and then I say, run another simulation, but it's 501 parts per million. We've only changed it by 1 more part per million. It isn't like we get a radically different climate, okay? We get basically the same thing. It's not like a weather prediction. There's no butterfly effect here to these climate predictions. Little changes in these external forcings, these boundary conditions, little changes to the albedo of the Earth, little changes to the amount of greenhouse gases in the Earth's atmosphere don't produce giant changes in the climate, the way a little change in the observations that come in from a weather balloon or something like that might make a very large change in the weather being predicted. Now, let's keep picking this apart here. Remember, the skeptics' argument was that we couldn't make these kinds of climate forecasts because we can't predict the weather 3 days from now. How are we going to predict the weather 100 years from now? And we said that the issue here is that weather and climate are two very different kinds of questions. The answer involved the fact that numerical weather prediction is an example of an initial condition problem, and climate forecasting turns out to be an example of a boundary condition problem. The climate that you predict depends on, the climate model ends up simulating, depends on the things that are the boundary conditions. Output from the sun, greenhouse gases in the atmosphere, albedo of the Earth, changes to the orbit of the Earth, although changes in the orbit of the Earth don't happen on like a human lifetime. Those are more like geologic time. And it turns out these kind of boundary condition challenges here are much, much easier to simulate farther into the future than an initial value problem is. We can simulate weather out to like maybe 5 days, maybe even 6 or 7 days or something like that. But once you get beyond that, the forecast doesn't have much skill. It's an initial value problem. On the other hand, boundary condition problems, like climate simulations, in fact, can be carried far farther into the future before the forecasts don't really have skill anymore. These terms, initial condition problem and boundary condition problem, are two very different kinds of problems that are actually the domain of a very scary discipline that you might not be comfortable with: differential equations. Differential equations, oh my goodness. Are you scared of math? I mean, you should be scared of math. Math is something students just like you are doing it, okay? Students just like you are in math, 500 level math classes all the time, and I just want to draw your attention, even if you don't know how to do these kinds of problems, to understand what these problems are for. There's a whole course at Creighton, Math 545, is called Differential Equations, or DiffEQ, and tons of students take it, okay? This is not something you have to be a math genius to do. It's just more math. It's the next thing you take after Calc 3, if you take Calc 1, and then you take Calc 2, and then you take Calc 3. If you are studying engineering, or economics, or chemistry, or physics, or atmospheric sciences, or any of a large number of other disciplines, the kinds of problems that you learn how to solve in your discipline are differential equations, and you have to take that class. Now, what is a differential equation? Because I know the vast majority of the people who are taking this class are never going to take DiffEQ, and that's fine. I want you to understand what the type of problem is, because initial condition problems like weather predicting and boundary condition problems like climate modeling are two different kinds of differential equations. Differential equations are a type of math problem in much the same way you had like algebra problems, or you had calculus problems if you took calculus or something like that. Most differential equations are a mathematical way of explaining and predicting how things change, how things grow, how things change their position, etc. They are based on the processes that force change. but they explain then things like the changes in the flow of water through a pipe, or the changes in the growth rate of a colony of bacteria on a petri dish, or the rate at which funds will grow in a different kind of fund, that an economist might know about, or something like that. They are just it's a mathematical set of techniques for explaining change. All right? That's hence the word differential of differential equation. I mean, it's about finding differences and how things are changing, like usually with respect to time. You all survived algebra. You know what it means to solve an algebra equation. You had a big old mess like 3x plus 7 equals 10, and then you solve for x where x was equal to 1. That was a solution to a differential equation. To an algebra equation. What is a solution to a differential equation? To solve a differential equation means using the equation to determine how things are going to change. I have this equation that explains how my air is going to be changing in temperature with respect to time. Solving the equation means now I know what the temperature is going to be. I have a differential equation that explains how many bacteria are living in my petri dish, and now at time t, I now know how many bacteria there are. That's what solving a differential equation is. Solving the initial condition differential equations that are a weather problem means finding out what is the temperature, the pressure, the wind, and so on at all these locations. Solving the boundary condition differential equation will mean something else. But we'll get there. But to understand, I'm going to explain differential equations using a map of Creighton. Okay, we're going to make a system here that we're going to be simulating, just like we'll simulate with a model the weather or the climate. Here I'm going to be simulating something that I'm going to just make it like a little game. I'm simulating, tell me where my position is. What's my location right now? And I'm here on campus someplace, and I'm going to follow some rules, just like there's physical laws that control how air parcels move in the atmosphere, or change the temperature of volumes of air, or whatever. I'm going to make some rules here. And these rules are of a form, in a differential equation, you wouldn't know like where I am at time t. Like 10 seconds from now, where will I be? What you know about is changes. I will be changing my direction in this way. I'll be changing my position in this way. Like I'll be walking forward, or I'll be turning to the right, or whatever. In a climate model, this might be my climate is warming here, but the ocean is maybe warming less quickly, or this ice over here is melting, and over here this ice is melting, or whatever. But let's just do some easy examples involving like a little problem of figuring out how we're going to be changing. In this case, we're changing our position. So let's first do a really easy example here. I'm saying in this easy example, let's say you have 3 instructions in this little game or whatever. It says walk 50 feet to the west, turn right, and walk 50 feet to the north. All right, well, is that enough information to tell you where you end up? Sure sounds like a pretty simple game, but it doesn't tell you where you're going to end up yet because you don't know where you're going to start. So like in the first case here, what did I have the person start? I had the person start at like 24th and Cass, and the first little red marker there. And if they walked 50 feet to the west and they turned right and walked 50 feet to the north, they end up kind of in front of, by the fountain someplace, okay? Or that person over there that I show marked with the sort of bluish-green markers there. If that person started, where are we here? It's down by those dorms or whatever, over by the soccer fields. And then they walked 50 feet to the west and 50 feet to the north. They end up kind of over there by Harper. Okay, you had to know your original position. Otherwise, these instructions don't tell you where you end up. This is an initial condition problem. These instructions just tell you how your position changes. And without being told where you started, what your initial condition was, there was no way to know where you ended up. Okay? But this was a pretty easy example here. In this case, the solution ended up being entirely dependent on your initial conditions and, of course, the rules of the game, as in, like, where do you start and so on. Well, this is kind of, and also the rules of the game as in, like, telling me I had to go 50 feet to the west and 50 feet to the north and so on. And weather forecasting is, in numerical weather prediction is a bit like this. We take the 7 primitive equations and they just tell us how things are changing. Like, the temperature's warming by this much, or the winds are turning in this way, or the pressure's falling in this way, or whatever. They tell us how things are changing, so as long as you have the initial conditions, you're going to be able to figure out how the weather's going to change. Okay, that's a very simple example of how we could take a set of rules, which are sort of like our analogy here to the equations, and we could find a solution to them if we knew where we started, our initial condition. But we can make the game more complicated and harder to predict. Here's a harder example. What if step 1 was walk 50 feet downhill, then turn north, and then walk 50 feet to the north? Oh, okay. Well, following those instructions, can I predict in advance where I'm going to end up? No, because I don't know where I started, and I don't know the lay of the land. There's nothing about these rules that tell me anything about like where there's hills and stuff like that. That's going to be about a boundary condition. That's something outside of the rules. Well, if I started with that little red marker there, let's see here. The little red marker is kind of in front of the Scott Center there. And if I walked 50 feet downhill from there, that would be kind of down towards Kiewit. And then I turned north, and walked 50 feet to the north. Looks like I end up over kind of by Riggy. On the other hand, the other guy, I can't think of the name of that dorm that's just off to the east of 24th Street, but that kind of bluish-green marker there. Well, downhill from there is east. And so if I walked 50 feet downhill, turned north, and walked 50 feet to the north, I ended up someplace completely different. Where I ended up depended on both where I started and the lay of the land. Where were the hills? Which I'm in no control of. I don't get to move hills to make me work out where I want to be in this game. That is a boundary condition to it. It's not part of the rules. I don't get to say so as to what the hills are, where the hills are, and where the valleys are. Now, if I follow this rule here someplace, I can actually come up with ways in which small differences in my initial conditions don't matter all that much. For example, if I take these two sets of markers here, on the first one here, the red guy here, if I started him just north of the Kiewit Center, Scott Center, kind of in front of the library, take him 50 feet downhill, turn him to the north, he ends up over by Riggy. What if I started somebody kind of closer right in front of the library? Well, 50 feet downhill kind of takes him over towards the humanities buildings. He turns to the right, and he ends up by the Riggy building. It doesn't really make that big of a difference. We started off pretty much at the same place, a little bit different, and we end up at pretty much the same place. Okay? Small differences in our initial condition, our exact position, didn't actually matter all that much in this example. But what about this one I drew right here? Now, this one's a little trickier here. I've got a red and a blue-green marker as to where I'm starting, and they're both kind of right in front of Creighton Hall, right by the top of the hill on the mall there. Well, the red marker there, 50 feet downhill, is to the west, and then I turn north, and then I turn and walk 40 feet to the north. Looks like I'm kind of, I don't know, I'm down kind of on that Anderson Plaza or whatever, where people play Frisbee and stuff. On the other hand, look at the green marker there. That's really close to where I started with the red one, but it's a little farther to the east. And we're just over, I'm trying to pretend here I'm just over the top of that hill right by Creighton Hall. Now, 50 feet downhill is going past 24th Street and over towards that dorm over there. And then I turn north, and then I walk 50 feet to the north, and I'm in that parking garage, or that parking lot just east of 24th Street. Look, I started off at practically the same damn place. But even that small difference in my initial conditions completely changed the outcome. Oh. This is a mix of an initial condition and a boundary condition problem. It mattered where I started, and it mattered the external processes acting, like where were the hills, and so on. Now, weather forecasting actually turns out to be a whole lot like this. Sometimes the forecast is good, even if there are, and there certainly are, some problems in the initial conditions. But other times we end up with simulations that don't look anything like the real world, because changes in the initial conditions and changes in the boundary conditions, we ended up with a simulation that didn't look anything like what the real world did. Let's try another really hard example. Here's another example of like we started at some location, we're going to follow 3 basic steps, and we're going to see where we end up. Okay. Alright, here's my 3 instructions. Walk downhill until you hear a dog. Face upwind and walk 50 feet. Those are strange instructions. Are they, based on those instructions, can you figure out where you're going to end up? No way. The paths are crazy and complicated. The red marker there that starts out in front of Creighton Hall, well, downhill is to the west, and then kind of down along Wareham Parkway, and then under the underpass under the Highway 75, and then, oh, well, hey, we heard a dog over here over by 30th Street, and we faced upwind, the wind was from the northwest, and we ended up at that red marker over there by the dog. But the blue marker there, okay, we were just past the crest of the hill on front of Creighton Hall, and now we're walking east, downhill, past 24th Street, past the dorms, past the Harper Center, past the law school, past the soccer field. Hey, we heard a dog. All right, now we've turned to face upwind, and we walked 50 feet upwind, and we ended up at that spot. Wow. This is being driven by all kinds of crazy... I mean, these two people started off practically at the same place and ended up on opposite sides of town. How did that work out? Well, this time it was strongly influenced by both the initial conditions and the boundary conditions. And real equations that get solved in differential equations, this can happen too. Where the future, where you end up, strongly depends on all kinds of things outside your control, like the boundary conditions and so on. But the game doesn't have to be hard. I don't want you to get the idea that that means, therefore, that anytime there's rules that are applied here that we are using to figure out how things change, anytime we have differential equations, like somehow or other predicting the outcome becomes impossible. No, not at all. Let me give you another example here. This one's going to be just a fairly simple thing. I kind of just wrote it as one step here. Walk downhill as long as it takes until your feet are wet with salt water. Okay? That's a pretty simple instruction here. And I'm going to have my two little people start right there in front of Creighton Hall. And the person in red is just a little bit west of the top of the hill there, and they're going to walk downhill, down the mall, past the student center, past Kiewit, past Gallagher, down under Wareham Parkway, around under this Highway 74, wherever that all takes. I don't know exactly which way is all downhill over there. Wow. And the person who's got the bluish-green marker there, he's a little bit east of the top of the hill over there by Creighton Hall, and he's going to go downhill over 24th Street, down past the dorms, past Harper, past the law school, and head off towards the soccer field, and he's walking downhill that way. And it sounds like these people are headed off in totally unpredictable directions, but if we zoom out a little bit farther, remember the instruction was walk as far as it takes until your feet are wet and it's salt water. All right, well, both people are going to be walking and walking downhill until they end up in the Missouri River. Okay? Downhill eventually means in the river. Alright? And in fact, if they keep walking, I don't know how, or swim here or whatever, I didn't really think this all through that well before I made the analogy here. If they just keep going and keep it going until they are wet with salt water, they're going to end up in one very specific place. The delta of the Mississippi River in Louisiana. That is, they're going to encounter the Gulf of Mexico down there. And it doesn't really matter where they started. The fact that they started close together, right next to each other at Creighton Hall, doesn't change the fact that they both ended up at the same place, and doesn't change the fact that at least at the beginning they were going in different directions. And heck, I could even take from my house in southern Indiana, and I could walk downhill until I get my feet wet with salt water, and I'd go down into Pigeon Creek, which is near my house, which would end up eventually in the Ohio River, which eventually would end up in the Mississippi River, and I would end up at the Gulf of Mexico too. See, in this case, where I started my initial conditions doesn't make a damn bit of difference. Here, the rules, the external boundary conditions of the game, like the lay of the land, is what's determining the outcome. Now, for this kind of differential equation problem, the initial conditions barely matter at all. Only the boundary conditions, like which way is downhill, mattered, and I'm not in control of that. That's something I would just have to tell the game, right? I would have to tell, if I was trying to simulate this in a model, I'd have to tell the model where all the hills were and the slope of the terrain and all that kind of stuff. I'm not in control of that at all. In fact, the initial conditions here barely matter at all. The only way they would matter is if you got outside of the watershed of the Mississippi, like if you got across the Continental Divide, like the black line there is in Colorado, well, then you would be draining towards the Pacific instead of towards the Missouri. But basically, it doesn't matter, over a large chunk of the country, it doesn't matter where you would start that game. That would be a very predictable outcome. As long as you started someplace between the Rockies and the Appalachians, I know where you're ending up. So, what is this telling us here? Let's think back to that skeptic's argument. The skeptic was saying, how does a scientist know they can predict the climate for 100 years in the future if they can't predict the weather 3, 4, or 5 days out into the future? And we said that the issue stems from the fact that weather and climate are two very different kinds of questions, and the numerical weather prediction one was an initial condition problem, whereas it turned out the climate type problem was a boundary condition problem. And it turns out both both initial condition problems and boundary condition problems can be very, very hard to solve with a numerical model. But in the case of the kinds of equations, the kinds of boundary condition problems that make up a climate model, it turns out that our ability to model the climate as a boundary condition problem is actually really good. It isn't like it takes unobtainably great initial conditions for a climate model to work, because in the end, the initial conditions don't matter one damn bit in the climate model. It is the boundary conditions that end up mattering in the climate model, not the initial conditions. And we understand the boundary conditions really, really well. Because the model depends on things we know, we can actually make that model work way far into the future. If it depended on the initial conditions, and we aren't very good at measuring the initial conditions and computing them, then we would have a problem. But climate isn't that way. Climate is a boundary condition problem. And it happens to depend on boundary condition problems can be a mess just like initial condition problems. But in the case of climate, the boundary condition problem isn't bad at all. It's kind of like that problem that we did with the map where we walked until we hit salt water. Okay? Actually, that wasn't so hard to figure out. It wasn't hard to figure out at all where you were going to end up with that problem. In the same way, climate problems, don't get me wrong, they're plenty complicated, but they're just boundary condition problems, and they're very manageable boundary condition problems. Now, just for the record here, I just want to point out this whole business of initial condition and boundary condition problems was not invented by climate scientists. Oh, it says on the slide was invented. Was not invented by climate scientists. This is all standard stuff that you learn in a differential equations class, and the same ideas apply if you're talking about engineering or chemistry or physics or anywhere else. That's why I'm telling you this stuff in an Understanding Science Module Core course, is because we're understanding that these are the kinds of problems and considerations you have to take into account, whether you are talking about the growth of some fund in your economics class, or you're talking about the spread of disease in an epidemiology class, or whatever. Any kind of system that is described by differential equations, which is pretty much anything in the natural sciences or economics or social sciences or anything, ends up being a class of problems like initial condition problems or boundary condition problems or whatever. Alright, before we move forward, let's do a couple more questions here. I just like to break it up a little bit. Question 5. True or false? Boundary conditions are a type of input to a climate model. Is that true or false? Good question, if I may say so myself. Alright, choose from one of the two below here and get a little feedback before you move on to question 6.